and then transmission gear reducer mechanism as well. And the second hardware is Marble. This is a climbing legged robot, okay? But it's actually very fast and agile. And this climbing legged robot capability is enabled by magnetic foot, which can provide about 500 Newton holding force. And then for this magnetic field, we utilize the electropermanent magnet, which is different from electric magnet. So if we use electromagnet for foot, you need to have electric energy, okay, throughout the in order to enable the magnetic force. Sorry, I think that my Zoom is logged out.
Yeah, you lost internet connection, I think.
Okay. Let's try one more time.
Yeah, sorry about that.
Okay.
Yeah, it works.
Yeah. And then this electropermanent magnet only need electrical energy when you make switching between on and off state. And then this this switching can happen in only 5 milliseconds. So it can be switched on and off very, very fast. Okay. So with this hardware design, we design our own control algorithm as well. The first approach we do is actually model-based design. And then the second approach we do is running-based design. Okay. And then today I will present mostly about the model-based control design. And then actually our majority of effort goes on to hardware design and then maintenance of hardware. Only less than 45% of my energy and effort goes to the control design. So I'm very sad that I cannot present about this work here, but yeah. But anyways, I will try to focus on more on to 45%. Yeah, the control design. So let's see what our robot can do. So this is high-speed running. And this robot was able to run up to 6.5 meters per second. And then it could finish the 100-meter dash within 19.8 seconds. And then we actually contacted the Guinness World Record to certify our record. So this is the fastest 100-meter by quadruped robot. Yeah, I mean, approved by Guinness record. Okay? I'm not sure it's important or not, but yeah. But anyway, so now we have the second version of the robot. This robot is actually even faster than the first version. So it can finish the 100-meter sprint within 11.6 seconds. And I believe this would be faster than all of us, right? Most of us. And then the maximum speed was 9.5 meters per second. And then I think this very high speed can be enabled because we design our own hardware. And to realize this, we have to take into account electric motor characteristic. And then in URDF, you can actually set the limitation of torque and the angular velocity. But if you set that, then it looks like this. So torque and omega motor is actually scale shape, but real electric motor operating region looks like this. So we actually in this paper accepted in the Robotics and Automation magazine, we introduced how to handle this motor operating region in reinforcement learning algorithm. And then you can see that it actually the algorithm utilize a very wide range of motor operating region, as you can see. And and then we have our own RL algorithm to enable various types of rough terrain walking. And then it can climb up 67 centimeter step up in the blind setting without utilizing any vision. And then this algorithm enabled a very natural looking galloping motion. But unfortunately, this galloping motion does not provide a higher speed than trotting motion. So it's probably something is going on between animal and then our robot. Yeah, we don't know why, but yeah, probably. So yeah, we don't have a spine. Yeah. And this robot can do bipedal walking. And this is actually pretty big. So the height is about this big. It is pretty scary to look at in bipedal mode. So the maximum speed was 3.6 meters per second. So it's already more than 10 kilometers per hour. And then it can handle a very brutal disturbance and then you can handle sideways pushes even though we don't have any degree of freedom for that. So this is all blind walking. And combined with the vision feedback, we can enable very fast running over the obstacle, as you can see. So in the wild and then as well as in the structured environment, something like this. So this height is 60 centimeters high. So all of this is actually designed by RL. And then I'll be talking about this. So we'll talk about the model-based algorithm. And then I only showed the very successful moment of our experiment. And then as experimental roboticist, we encounter a lot of great failure moments. Okay, so I did my PhD at Michigan, and then this is my robot Mabel, and then you can see that leg broken. This is actually nothing. This is yeah. So there's a fire, very smoke. I'm not sure somebody like this video or not. So but anyway, so. And we have a MIT cheetah too, and then it suddenly do some weird behavior. And now I know why it does that. And then we have a KAIST hound. And actually, there was actually safety switch, and then somebody forgot to press that safety switch, and then he chose actually that was me. So I couldn't blame my student. But anyway, so these are all the catastrophic failure moments, and then actually these two moments actually enabled me to think about better idea of model predictive control. So we will actually get back to that later. Okay. So for model-based control design, we utilize a model predictive control, and then we have a real function, and then we have a state transition model, and then we have a constraint. By solving this optimization, we can obtain the sequence of the control input. Okay, and then I mean probably everyone here already know about how the MPC works. So I will skip this slide. But this optimization problem should be solved around within 10 milliseconds or 20 milliseconds in order to respect the real-time capability, real-time constraint. And then the model here is too complex. So in most MPC algorithms, people reduce model complexity by lumping all the small inertias into the big inertia. And then in this model, the control input is ground relation force instead of a joint torque. Okay. And then there is of course, no contact and friction dynamics in this model. Okay. So you can greatly simplify the model. And then further, usually foot contact sequences are given, predefined before you run the MPC. Okay. So you select trotting or bounding and then galloping. I mean, you can introduce a mode and then you can switch the mode between the controller, but these foot contact sequences are usually given in order to save your time, okay, in order to decrease the number of control inputs, okay? And then for these two robots, KAIST hound and then Marble, we want to have a single controller to control these two robots, even though the robot looks very different and the robot's configuration is very different. So we use a single rigid biodynamics, and then we need a different foot contact constraint for different robot. So this robot has to respect Coulomb friction, and then that robot has to respect the magnetic field constraint, okay? And then we have a rotation matrix variable in manifold, which is in the optimization problem. And then people usually use Euler angles. So it was okay if your robot only works on the flat surface, around the flat surface or sloped surface. But our robot has to go through like global orientation. It can go through the vertical orientation and the inverted orientation. So as you know, Euler angle has a singularity in the vertical configuration. I mean, you can reset the Euler angle if you want, but we don't want to switching in our control design. And then that experiment that I showed the tumbling, this is actually because of Euler angles. So I chose wrong Euler angle. Some Euler angle singularity when U becomes 90 degrees. Okay. Actually, I did study very well or thoroughly robot dynamics class, and then I selected the wrong Euler angle. Okay. So this is the result when you choose wrong Euler angle. Actually, that actually turns into the idea we published into IEEE TRO in 2021, and then IROS, and then won the best paper award, one of the best paper at the IROS. So our idea is just utilizing the rotation matrix for MPC formulation. Okay, so we carefully formulated the MPC problem utilizing rotation matrix, and then it becomes optimization on SO3 manifold problem. And then we use reparameterization trick in the unit using retraction map, logarithm map and exponential map. And then to solve this optimal problem efficiently, you need a gradient and Hessian information. And then that gradient and Hessian information, we obtained this from this paper. This is a very seminal paper by Forster et al. And then we utilize the Gauss-Newton Hessian matrix. Okay. Now this, so now we formulated our own SQP solver, and then we have our own QP solver. At that time, we didn't have a OSQP. Okay, we didn't have a good QP solver which run in embedded system. So we decided to develop our own QP solver, and this QP solver utilizes interior point algorithm. So it's actually numerically very stable. And then the solution quality is actually very consistent. And then I heard some complaints of utilizing the OSQP. The quality of solution is not very consistent, but our solver is consistent. And then the speed is actually a little bit slower than OSQP. Yeah. And then this is available open source. We open sourced it. And this is MPC. It run with the speed of 3 meters per second. And it can recover from very strong push by me. So it even recover, even though it has a very slippery surface like that. Yeah. And we transfer this algorithm to marble robot by only changing the constraint, foot contact constraint. And this is the marble robot climbing on vertical surface. The maximum speed was 0.7 meters per second. And then if you rotate this video 90 degrees, you cannot actually differentiate with the flat ground working and the vertical working. So this is that fast. And then you have an inverted throat gate. And then you can handle 2 kilogram payload. So this limitation of payload is not because of the magnetic field, it's because of motor torque. Really. Yeah. And then with some very simple motion planning, we can make it overcome some obstacles. And this capability is not available in wheeled vehicle. Okay. And surface transitions. And then we do some outside experiment. So this surface, the surface of a water tank is covered by very thick paint, but our magnetic field is strong enough to have enough holding force. And this framework is extended to estimation. So we have an invariant smoother as for state estimation. Okay. But now we go back to the failure video. So this failure is caused by this wrong foot placement into the static area. Okay. So, but even with this very unexpected situation, this robot does not have the ability to change its foot sequence. Okay, it's probably better to change the foot sequence to handle this disturbance, right? So we tried to now include the contact mode into our MPC. So, and then this was published in IJRR recently. So now we formulated our MPC problem with differential dynamic programming. And then, of course, we needed our contact model. And then our contact model, we utilized the contact model presented in this paper. Probably this is not original paper to have this model, but anyway, so we took the model from this paper. And then the Contact-Implicit is actually solution of this optimization problem, which has a complementary constraint and then Coulomb friction cone. And because of complementary constraint, the solution for the normal pulse, normal contact impulse, categorized into 3 modes: okay? Separating, clamping, and then sliding. Okay, and then for each mode, we utilize this constraint to derive an analytical gradient. Okay, but the problem is actually analytical gradient in clamping mode. Okay, so because this analytical gradient should satisfy that condition where the after contact velocity should be 0. This gradient is always 0. Okay, and then it will create the problem local minima. Okay, so for example, in this video, this robot starts with the clamping mode, and then it has to reach the reference position, which is actually higher than the leg length. So it has to jump. It has to break the clamping mode. But that gradient does not have that information. So if you run the MPC in this configuration, it does not jump. It just stays there because the gradient is not informative. If you have a correct gradient, but which is not exact gradient, then you will have this periodic jumping, automatic periodic jumping. Okay. So if you see the gradient and then the optima in this diagram, so this is a very simplified problem. You can see this initial condition leads to this local minima. Okay, so our idea is actually comes from interior point algorithm, where the complementary constraint is relaxed to smooth the complementary constraint. And then you have a parameter law, which actually you can adjust the smoothness of the relaxed constraint. And then with this, you can see that our algorithm produces this nice looking periodic jumping to match the reference point as much as possible. And then if you see this diagram, when rho equals 0, we have still local minima. As we increase the value of rho, we point all the initial point toward to the global minima. Okay, so this is not guaranteed. We don't have any guarantee, but for this simple example, it works. Okay, but if you increase too much, then the convergence point is different from global optima, of course. Okay, so if you have a too small value of rho, it's the same. If you have a too large value of rho, then it rush too much to jump up. But we have a very wide range of value of rho, which provides a reasonable result, okay, performance. And then we integrated this smooth gradient with the differential dynamic programming. For the path, we use the original complementary constraint. So we only utilize the smooth gradient, analytical gradient for backward path. Okay. Of course, we utilized the Pinocchio library, and then we will test that IFG code for this. Okay. Yeah. Anyway, so and then to increase the convergence property, we utilize the feasibility driven DDP. Okay. Now this is the result. So this is the reference trajectory. As you can see, there is no motion. There is no. So this motion is actually very, very trivial. Okay, there is no swing motion. There is no very complex motion in the body. And this is the emergent behavior, emergent contact sequence. We do not provide any clue into the contact sequence, any initial condition. And this is a slippery surface. As you can see, it slides down. When it steps behind, it propels, okay, to catch up. And then this cartwheel motion, you can do that. And then we extended this into 3D motion, and then we need some more forms in the reward. For example, we need to have a symmetric cost. I mean, this is actually I think in RL this reward function is very popular as well, right? So if you have a symmetric cost for trotting, then it provides a trotting gait. If you have a symmetric cost of pacing, then it provides pacing gait. So we don't have any other reward actually. We have only symmetric reward about the gait. And then we have very trivial reference for X and U. Okay. And then this code is actually inherently unstable because the center of mass is not on the supporting region, but it wants to keep that pose as much as possible. And then the humanoid motion can be obtained very easily. Okay, so now experiment. So we implemented this algorithm to real robot, and then the sampling time is 40 Hertz. And then in this implementation, we don't have a swing leg trajectory. We don't have a sophisticated, very detailed body motion. So all of this motion comes up from NPC in real time. And then it can be solved in with the sampling of 40 Hertz. And then this motion, rearing motion can be done as well. It's not as good as a simulation, but it tries. It tries to match the reference point. And then now we are utilizing this smooth gradient for friction coefficient identification as well. So here we want to obtain the coefficient of friction mu by comparing predicted from dynamics and then measured states. And then we utilize a gradient-based strategy to obtain this. But the problem is, so this is the space of the lambda and after contact velocity for friction. But in clamping mode, the lambda is not a function of mu. Okay, lambda is a function of mu only when sliding mode. So that's the problem. So in clamping mode, you don't have informative gradient. Okay. So there is no update, even though the predicted x and then measured x is different. Okay. So we introduce a smooth friction model, and then as you can see, we can actually adjust the smoothing parameter as well. So we utilize this model to identify the friction coefficient parameter, and then this is the result. And this paper is still under review, RAL. So if we use original analytic gradient, the coefficient friction parameter does not go down actually once it becomes clamping mode. Anyway, so we tried to also utilize this to manipulation problem. This is still in simulation in the very simplified model. And then with that, I want to conclude my talk.
Yeah. Great talk. I want to ask about state estimation. How much of a role does that play in the quality of your controllers?
It's really important, actually. So the performance in simulation and performance in real experiment is very different because of quality of state estimation. So we didn't utilize any like motion capture system for that experiment. So the performance of the MPC is very sensitive to the body height estimation. Once it misses the contact, yeah, as you know, the contact sequence will be really different from previous state. And then the MPC has a harder time to getting good solution. Okay, so it happened.
I have a question about your the friction estimation.
Yes.
Coefficient estimation. So I noticed that like when it goes to a new domain, it slips a little bit. That tangent force is really what allows for proper identification of that mu. But how do you compromise with it, stability with
Okay.
on that?
Actually, we didn't utilize the estimated coefficient friction for MPC. It just identify, so it does not change it. So that's why it makes slips. So that could be next direction. Yeah.
Have you thought about adding, like you're using the first principles to model your system, physics-based methods? Have you thought about having learning neural network on top of that to compensate for the residuals you see, especially that you do lots of experiments and you can collect data from that?
Yeah, that's another direction that I push my student as well. So I mean, this method is not robust. I mean, RL method is very robust. Even though we have a simple real gap, RL method can become very robust if we utilize a domain innovation or something like that. So we do not have that here. So I actually asked my students, why don't you add a residual policy, like residual RL policy, and then train in randomization, but most of the actions come from the DDP. But already this method provide sample horrible sample inefficiency because adding that into your RL increase computation time a lot. And then we do not yet have a parallelizable solver. And then I'm not sure we have a parallelizable QP solver, GPU, running GPU. Yes, so just tell me, just advise me if you know one. So that's why I mean, I don't know. I mean, it's difficult actually. Yeah.
I think we'll go to the next speaker now.
Yeah.
So thank you again, Hae-Won Park.